In this lecture, we are going to find some important examples of Lebesgue integral, and then we are going to prove Lebesgue's dominated convergence theorem. This is also a very important theorem from the example points of view, So we are going to do lots of example, nice, interesting example, and then we are going to, prove this theorem, dominated convergence theorem. All right. So these examples are elementary, and they are going to be used in finding out the integration of a complex function like that, Lebesgue integration of complex function. So let us see some of the important, example. All right. So that if f and g are measurable, and then modulus of f is less than or equal to modulus of g almost everywhere, and g is integrable, then f is integrable. Okay, f and g are measurable, modulus of g is greater than or equal to modulus of f, but g is integrable, then we are going to show that f is integrable. So prove it is given that modulus of f is less than or equal to modulus of g almost everywhere, and you put e is equal to x such that modulus of f not less than or equal to g, then since it is almost everywhere, measure of e is equal to 0. Now measure of e is equal to 0, then we define f prime, a new function, is equal to f of x if x belongs to complement of e, g of x if x belongs to e. Alright, so f prime is measurable. From the definition clearly, f prime is measurable, and modulus of f prime is less than or equal to modulus of g, and f prime exactly equal to f almost everywhere. F prime is equal to f almost everywhere. Alright, if f is measurable, f prime will be measurable. Okay, so now positive part of f prime will be less than or equal to modulus of g. Similarly, negative part of f prime will be less than or equal to modulus of g. So then, but g is integrable, therefore it's finite. Therefore, positive part's integral is finite. Similarly, negative part's integral is also finite. So therefore, since f prime is equal to f almost everywhere, we have f prime positive part is equal to f positive part almost everywhere, f prime negative part is equal to f negative part almost everywhere. Alright, so integration of f prime, positive part of f is exactly equal to integration of positive part of f prime, but this one is finite. Similarly, this one is exactly this one, but this one is finite, and therefore both are finite. Okay, and it shows that f is integrable. Alright, so that if f is integrable, then the modulus of the integration is less than or equal to integral of the modulus function. And now we are going to find out when does this equality holds true. When does the equality hold? Alright, let us prove this. Modulus of f is greater or equal to f, that is pretty simple. And then modulus of f minus f will be greater or equal to 0, simple. So therefore integration of modulus f dx will be greater than or equal to integration f dx, that is also very simple. And also modulus of f is greater than or equal to minus f, so modulus of f plus f will be greater than or equal to 0, and therefore we have this one. And combining these two, we get this easily. In the modulus integration f dx less than or equal to integration modulus f. Okay. Next, we find the necessary condition for the equality. Alright, so let us see. Integration of f dx will be greater than or equal to 0, and then if this part is positive, then whether you take modulus nothing but if since this is positive, so you can take out modulus. That is what integration modulus f is exactly equal to this one, and then this implies and implied by if this is true, then integration of this function is equal to 0, and that means what? This is actually equal to 0 almost everywhere. Alright, so that is f is greater than or equal to 0 almost everywhere, and that is the necessary condition, one of the necessary condition. If integration of f dx is less than 0, then if you drop the modulus, negative will be come out here. Alright, that means this one is exactly equal to this one. So this implies and implied by this integration is 0. That means the function is 0 almost everywhere. So that means f is less than 0 almost everywhere. So They are the condition. Therefore, f is greater than or equal to 0 almost everywhere, or f is less than or equal to 0 almost everywhere, and this is a necessary condition, and it is also sufficient also for this equality to happen, because since it is implied by, it is both necessary and a sufficient condition, and that is what we wanted to find out. Okay. Another example. So that if f is integrable, then f is finite valued almost everywhere. If f is integrable, f cannot be infinity on non-measurable set. That is what this example means. Suppose not, let us assume that it is not true. That means f is equal to infinity, modulus of f is equal to infinity on a set E whose measure is not equal to 0. Alright. So that is, since it is for infinity, it is greater than any natural number, modulus of f is greater than n on E for every positive integer n. So therefore, integral of f will be greater than over E, this one, but n dx. But n dx, the n is natural number, m is non-zero, so this is non-zero. But you can increase n unboundedly. Therefore, this integration is going to be infinity. Alright, it follows that f is not integrable. That means f is not integrable. So f is not, if modulus of f is not integrable, then f will not be integrable. A contradiction, and therefore this our assumption modulus of f is equal to 0 on a set with measure non-zero is wrong. Okay. Lebesgue's dominated convergence theorem, and this is also one of the important theorem. Let us see the statement first. Let fn be a sequence of measurable functions such that every member of the sequence whose modulus is less than or equal to g, that is, g is dominating every member of the sequence, where g is integrable, but this g is integrable, and let limit fn is equal to f almost everywhere. Limit fn is equal to f almost everywhere, then f is integrable, and its integral is equal to limit taking outside and limit taking inside is your f. Okay. So that is one of the very important theorem. Let us see. It is given that the functions are dominated by g for each n. So its limit is also will be dominated by g. Limit fn, and that is f of modulus f is less than or equal to g almost everywhere. Alright. Therefore, f and fn are integrable. Both f and fn are integrable. Alright. So the sequence of this sum g plus fn is a sequence of non-negative measurable function, because this is maybe negative or positive, doesn't matter, but g is positive and g is greater than that one, so their ultimate sum is non-negative. So it is a sequence of non-negative measurable functions. So by Fatau's lemma, we can apply Fatau's lemma. Limit infimum taking outside will be greater than limit infimum taking inside. Alright. So this implies that integration g dx plus limit infimum outside will be greater than or equal to integration g dx, this one. But this is integrable, means this is finite, you can cancel out. So ultimately what you get, limit infimum outside will be greater than or equal to limit infimum inside, since this one. So limit infimum inside is your f, and let it be inequality number 1. Again, g minus fn is a sequence of non-negative measurable function. So again, by Fatau's lemma, we have limit infimum outside will be greater than limit infimum inside. So, but this is actually equal to, if the negative is going to take out of the limit infimum, the limit infimum will be converted into limit supremum here also, okay. So after simplification again, you have this one. So let it be inequality number 2. From 1 and 2, what do we have? From 1 and 2, we have the result. Okay. Another theorem. It is about the series. Let fn be a sequence of integrable function. Now it is non-negative. Non-negative part is dropped. Okay. So it is a sequence of integrable function. Then so this summation n going from 1 to infinity, integration modulus of fn is less than infinity, means this is integrable, and then the series converges almost everywhere. its sums fx is integrable, and integral of the sum is exactly equal to, you know, summation outside the integration fn dx. Right. So this is also important. Let us put phi x is equal to summation n going from 1 to infinity integration modulus fn, and sequence modulus fn being a sequence of non-negative measurable, and they are also integrable also function. We have what we have. You can take summation outside n going from 1 to infinity integration modulus fn dx, and then you can take summation inside also, okay, because these are non-negative measurable and integrable function. Okay, so it implies that integration of phi dx exactly equal to integration summation n going from 1 to infinity modulus fn dx, but this is less than infinity, it is given. Okay, so phi is finite valued almost everywhere according to the previous example. It follows that summation n going from 1 to infinity fn dx is absolutely convergent almost everywhere, and modulus of f is less than or equal to phi. So f is integrable because this one is integrable. We have done that earlier, and so f is integrable. So we can write g n x is equal to summation I running from 1 to infinity phi x. You know, so this should be not infinity. This is n. That is a print mistake. Then typo mistake. Then g n x is less than or equal to phi x for each n, and limit g n x is exactly equal to f of x almost everywhere. So by dominated convergence theorem, what do we have? We can apply here dominated convergence theorem because every member of new sequence gn is dominated by this integrable function. So by dominated convergence theorem, what you have? Limit taking inside, that is f is exactly equal to limit taking outside, this one. But gn is sum. That sum you can take outside, and limit n tends to infinity means you can put here infinity. So that is the result. Example, let us say if f is bounded measurable function on a closed and a bounded interval, this one, then it is integrable, because we are going to compare Lebesgue integration and Riemann integration. Okay, Riemann integration is defined on bounded closed interval, and let us see if f is bounded measurable function on a closed and a bounded interval ab, then it is integrable. Let us see, there exists some positive number m such that since this bounded, you have modulus of f is less than or equal to m on ab, and therefore modulus of f is less than or equal to chi ab times m, and this is a measurable and is a measurable simple function, this one, and therefore integration ab modulus f dx is less than or equal to m times b minus n, that is less than infinity, and f is integrable, hence f is integrable. Alright. Example, if f is measurable and g is integrable, alpha beta are real numbers such that f is less than or equal to beta, but f is greater than or equal to alpha almost everywhere, then there exists gamma in between alpha and beta such that integration f modulus z is exactly equal to gamma times integration modulus of z dx. Alright, so this is also very interesting example. Solution, it is obvious that modulus of product fg is less than or equal to modulus alpha plus modulus beta times modulus z almost everywhere. Alright, so it shows that modulus alpha plus modulus b times modulus z is integrable. Alright, so therefore this integrable, it is dominating this one, therefore fg is also integrable, and therefore alpha times modulus z less than or equal to f times modulus z less than or equal to beta times modulus z almost everywhere, therefore their order of integration maintains like this. So if in modulus of integration of z is equal to 0, then z is equal to 0 almost everywhere. In that situation, integration f modulus z is equal to 0, and then f times modulus z is equal to 0 almost everywhere. In this case, the result is trivial. Suppose the integration of modulus z is not equal to 0, and then you can take gamma is equal to integration f times modulus z dx divided by integration modulus z, and clearly this number is in between alpha and beta, hence the equality holds true. by multiplication, cross multiplication, you have this one. Another example, if f is measurable and measure of E is finite and f is in between A and B, okay, f is bounded on E, then A times measure E is less than equal to integration f over E less than equal to B times measure E. Alright, solution, it is given that f is bounded on E, so therefore this inequality holds true on E, and these are measurable, they are integrable also. Alright, so therefore f chi E is integrable by the above result, and their integral maintains the inequality like this. Hence this one is A times measure E and this one is B times measure E, like that. Okay, so another example, for is xi in closed interval AB with AB are finite number. So let f xi be a measurable function and the modulus of f xi x is less than equal to gx, where g is integrable function, and limit xi tends to xi naught, f xi x is equal to f of x, where xi naught is in AB closed interval, then f is integrable and limit xi tends to xi naught, integration f xi dx is equal to integration f dx. So here we are doing, we are applying the dominated convergence theorem in parameter form. Okay, so let fn xi n be any sequence in AB, limit xi n tends to xi naught, then sequence f xi n is a sequence of measurable function satisfying dominated convergence theorem. This sequence is a sequence of measurable function satisfying dominated convergence theorem. So this is true for every such sequence which is converging to xi naught. Alright, so we can apply the theorem. So therefore f is integrable and limit n tends to infinity, integration f xi n dx is exactly equal to, you take limit inside integration, but when you take limit inside integration, that is nothing but your f. Alright, so example, if f is integrable, then integration f dx is exactly equal to limit a tends to minus infinity, limit b tends to infinity, integration ab f dx. Okay, so this is also for practical purpose of using Lebesgue integral. This is also very important. Okay, so that is exactly equal to, you can interchange the limit b tends to infinity, limit a tends to minus infinity, like this. Okay, so proof, we can write a to b f dx in this form. So you can easily verify this, you can write like this, and then now we have limit a tends to minus infinity, this exactly equal to this one. Alright, so therefore limit a tends to minus infinity, this one exactly equal to limit a tends to minus infinity, and this one, but this is exactly equal to minus infinity b f dx. Alright, similarly you can write in this form. Okay, likewise we can show that this limit a tends to minus infinity, limit b tends to infinity, integrand a to b f dx is equal to this much. Alright, so another theorem, if f is continuous on a bounded interval, closed interval AB, then f is integrable. Okay, if f is continuous, then f will be Lebesgue integrable, and its integral is denoted like this. For any point x in between AB, let it be denoted by capital Fx, then this Fx is differentiable function such that differentiation of f, capital F, is equal to f of x. So this is very interesting result. We know this result in Riemann integral, and this is about Lebesgue integration also. Okay, so proof, as f is continuous, it is measurable and bounded on AB, and therefore f is integrable on AB. So here integrable means Lebesgue integrable on AB. Alright, so for x in AB, this, and for small h, so that x plus h here, so you can choose, since x is in here, and you choose h very small, so that x plus h is in here again, and then f of x plus h, by definition this is equal to difference of these two integral. So but according to the theory we have developed, you can convert to positive, okay, by interchanging this limit, and that is exactly equal to integration x to x plus h f t dt. So since f is bounded on x plus h, so there are AB such that a less than equal to f less than equal to b on this one, f is measurable and 1 is integrable. The constant function 1 is integrable. So we are going to apply that example. So therefore integration x to x plus h ft modulus 1 dt is equal to gamma times this one, and that is actually to h gamma, where gamma in between a and b. All right, since f is continuous, there exists xi in here such that f xi is equal to gamma by, this is coming from the intermediate value theorem. So you can write this is equal to h gamma, but gamma you can write f xi like this. All right, so ultimately what, for h not equal to 0, dividing by h, we have this one, h as limit h tends to 0, that this is the differentiation of capital function. All right, so and that will be differentiation at xi. All right, so limit h tends to 0, we get what, you have this one. You can this xi you can remove replace by x, it doesn't matter. So this one. All right,